This video will deal with electrodischarge machining as a thermal, non-traditional machining process. The outline will include introduction to EDM, spark description, EDM machine, EDM pulses, electrode polarity, electrode wear, material removal rate and surface finish, EDM electrodes, EDM dielectrics, heat affected zone, factors controlling EDM in addition to EDM application. EDM is a thermal machining which involves the application of very intensive local heat to remove material by melting and evaporation of a small area at the workpiece. Many thermal machining processes are existing. One of them is electrodischarge machining, laser beam machining, electron beam machining, and plasma beam machining. These all are categorized as a thermal machining processes. EDM concepts relies on having a tool electrode and a workpiece immersed in a dielectric fluid. The tool is fed using a servo control system which maintains a constant gap between the tool and workpiece. Due to the occurrence of sparks, minute materials are removed by these sparks, and by time we will get the shape of the tool covered completely in the workpiece. The machining debris coming out of the sparks is flown outside the machining gap. During a single spark in EDM, we have ionization of the dielectric to positive and negative ions. And due to the potential difference between the tool and the workpiece, some will move to the cathode and other will move to the anode. And they move at high kinetic energy. They bombard the material of the workpiece and the material of the tool, creating melting and evaporation. At the end, we'll get craters formed by a single discharge or a single spark. Some of the molten metal by this spark will not have time to be ejected as a debris or solidified metal in the dielectric and re-solidify, causing a recast layer. And this recast layer is very hot. It will affect the bare metal of the workpiece, causing the heat affected zone, as you can see in the figure. The machining system of EDM comprises a pump which pumps the dielectric liquid after being filtered inside the machining gap. We have the tool holders, servo control feed which maintains constant gap during EDM. We have a pulsed power supply, DC generator in a pulsed form, and you see at the top the sparks are occurring at the narrowest distance between the cathode tool and anode workpiece. At the left hand side you can see the most recent EDM machine with the power supply and control system and the electric container. We can have two power supplies during EDM. The most popular one is the pulsed power supply, which produces pulses at different on times, off time, with different peak currents, and the frequency of discharges or sparks varies between 500 to 5,000 sparks per second, and the gap between the two electrodes is controlled by the servo mechanism and maintained at a constant level of 200 to 500 microns. There is another type called the RC power supply, or resistance capacitance power supply, which generates the form shown at the right hand side of volt with time. We'll have a charging time and discharging time for each pulse. So power per pulse in this case is smaller than that used in pulsed power supplies. And the main advantages of this type of power supplies is producing cavities, having thin walls and fine features. They can machine difficult geometries. EDM is not affected by the hardness of the workpiece material. This is a general remark of EDM. The process is par-free. When we come to the electrode polarity, we can have either the tool connected to positive or negative or positive, and the workpiece as well can be connected to positive and negative. This is not the case similar to ECM, where the tool must be negative and the workpiece must be positive. So depending on the electrode material and workpiece material, we can have a proper combination of the electrode polarity. For example, for workpiece material of copper, this should be all the way, irrespective of the electrode material, should be negative. Due to the occurrence of sparking, a material is removed from the workpiece, and at the same time, a lower material, smaller material is removed from the electrode tool. Therefore, there is an electrode wear occurring during EDM. The wear rate of EDM electrode can be calculated by this equation. We have three main types of wear occurring during EDM. We have the corner wear, we have end wear, and we have side wear. So there is a wear ratio, which is the ratio of material removed from the tool to that removed from the workpiece. This can be calculated by the equation of the wear ratio RW. And this formula is applicable for pulsed power supply. When we use the RC circuit or the RC power supplies, we can calculate the removal rate using the equation VRR. We can calculate the discharging current. We can calculate the discharging voltage as a function of the supply voltage according to the electric circuit shown at the right. And for maximum power delivery through the gap, the discharge voltage must be 0.72 of the supply voltage. The expected surface roughness can also be calculated in terms of RA as a function of discharge voltage and the capacitance used. For pulsed power supply, again, the material removal rate VRR can be calculated by this equation, while the average surface roughness can be calculated by the equation of RE in terms of the pulse current and pulse duration TP. Generally, the depth of damaged layer can be calculated as 2.5 the surface roughness RE, and RT can be considered as 10 times the value of RE. The graph shows the increase of removal rate increases the surface roughness, and this will be explained later through the crater size formed during EDM. We have a variety of EDM electrodes with different properties. We can have copper, graphite, tungsten, iron electrodes, and each material of the workpiece should accommodate a certain type of electrode tool material. They can be of different shapes and sizes. At the left-hand side, you can see graphite electrodes with different shapes, and at the right-hand side, you can see different copper electrodes. This type of material is machinable, so you can get any shape of the tool in accordance to the shape required in the workpiece. The dielectric used in EDM should possess adequate viscosity, high flash point, good oxidation stability, minimum odor, low cost, and having good electrical discharge efficiency. The craters formed in EDM depends on the pulse current and pulse duration. At the left-hand side, the increase of pulse on time increases the volume of crater, and this will increase the removal rate and accordingly will raise the surface roughness. At the right-hand side, you see the effect of pulse current for the same pulse on time. When you put more current in each pulse, you get larger crater size, larger removal rate, and rougher surface. The heat affected zone is created because the molten metal created by each discharge is some of it is resolidified and forms the heat affected zone. The discharge temperature in a single spark reaches 8,000 to 12,000 degrees Celsius, causing metallurgical changes to the workpiece surface layer, and a thin recast layer of up to 25 micron is created. This is shown in red, and the depth of a knead layer ranges from 50 micrometer for finish EDM to 200 micrometer in rough EDM. Rough EDM uses longer pulses, large current, generates larger craters, and consequently larger depth of a knead layer. There are many factors that control EDM. One of them is the pulse characteristics, such as pulse on time, pulse off time, duty cycle, pulse current. Some other factors are related to the electrode material, movement, the wear that occurs to the tool electrode, the workpiece thermal properties, because this is the thermal machining process. So the mechanical properties are nothing but the melting point, boiling point, electrical conductivity, and thermal conductivity plays a major role in controlling the removal rate, surface quality, and accuracy. The dielectric properties as well affects the removal rate, surface quality, and machining accuracy. Come to the main applications of drilling, as you see in the figure. Irregular taper, curved and inclined holes can be machined at typical feed rates of 0.1 millimeter per minute. For drilling, up to 0.5 millimeter diameter, leaving an overcut up to 50 microns. Cooling channels in turbine blades is one of the applications of EDM drilling. In such a case, we can use a numerical control system that enable large numbers of holes to be accurately located. Die sinking and milling by EDM. At the left-hand side, this is a die sinking. We have to manufacture this electrode using CAD system, but at the right-hand side, we can use a rotating electrode, very simple, but this electrode will generate the same profile in the workpiece using the electrode pass by the numerical control technique. So here we are using simple electrode, but at the left-hand side, we are not using a simple electrode. This electrode must be manufactured in advance. Wire EDM is an example of EDM machining, where we use a wire electrode traveling across the machining gap. The wire, we apply a pulsed voltage and supply the dielectric to the machining gap. Using the CNC movement, we can cut two-dimensional profiles in any conductive material using traveling wire EDM. At the right-hand side, you can see the machine of wire EDM with control system. We have here many variables: the wire speed, wire diameter, wire tension, power supply characteristics, pulse on time, pulse off time, pulse current. The feed is controlled by a servo control system, as the case of sinking by EDM. These are typical applications of wire EDM. EDM sewing using band saw or disc saw are shown in this slide. So the disc saw is rotating at speed and all should be immersed in a dielectric fluid. This dielectric fluid can be deionized water. EDM texturing is another application where the rolling EDM texturing is another application where rolls used for sheet metal rolling are textured with a certain pattern using EDM electrodes. And these rolls will be used later on in rolling sheet metals, which is used in car industry. Having a textured steel sheets will enable easier painting of the car bodies. Electrochemical grinding is an application of EDM. Remember, this is not a hybrid process. It is purely EDM using non-abrasive metallic wheel. So the main material removal mechanism is sparking or electrodischarging. Micro EDM by wire electrodischarge grinding is another application. This process can be used to machine EDM electrodes with diameter down to 5 microns and depth to diameter ratio of 30. The process can be used to machine electrodes having a square cross section, 50 by 50 micrometer square, that are used to produce sharp cornered cavities and slots. Micro punches that are used for mass production or of inkjet printer heads. Micro EDM is another application of EDM to machine conductive material of small size featured down to few microns. We can machine holes with high aspect ratio 5:1 in oil, 10:1 in the deionized water, 18:1 using special method, 100 micro-ohm in diameter in stainless steel. The process is useful for die and mold production. This is not suitable for mass production due to high tool wear. Typical applications of micro EDM and milling, drilling, inkjet nozzle fabricated by micro EDM. Micro EDG is another application of pure EDM used for machining long channels of 900 micrometer deep and 60 micrometer wide with closed ends in both sides of the stainless steel plate. Vibration assisted EDM is another application. We can use two methods, direct workpiece and tool vibration, and according to that arrangement, during the down movement of the workpiece will allow the entrance of clean dielectric, while the upward motion of the workpiece, the dielectric fluid plus the debris is bumped away from the machining gap. The material removal rate increased by 23% when we use 600 Hertz and amplitude of 0.7 micrometer. The surface roughness of vibration-assisted EDM is lower than the normal EDM. Similarly, the tool wear rate of vibration-assisted EDM is much smaller than that of normal EDM without vibration. The main advantage of using the direct vibration of tool and workpiece, we can get faster and more stable machining, can get better form of accuracy, we can get superior surface finish, high aspect ratio, more complex structure, increasing the percentage of effective discharges while avoiding the existence of arcs, minimum micro cracks of workpiece, which improve the fatigue life of parts, EDM stabilization with superior surface finish, increasing the machining speed by 40%, increasing the efficiency to 8 times greater than micro EDM, decreasing electrode tool wear rate. Vibration assisted EDM using the indirect method is done by the application of indirect ultrasonic vibration through the pressure waves within the dielectric at an angle 60 degrees. This will increase the process speed by 50%, as you see at the right hand side of the slide. Thank you.